So this will be additional video on chapter 2, linear models. This is not going to be directly included within our midterm, but this is, I think, maybe some part will be mentioned, but still this is just additional information on how we are going to use the linear equation or the differentials to solve some real problems. Okay, so we are going to start with this growth and decay models, and we can take this as a initial value problem as dx over dt equal kx. So we can start with defining the k as a constant, or we usually write constant of proportionality. Okay, so this will be our constant for explaining growth or decay phenomenon. Okay, like in biology, we can describe as in population of bacteria, small animals, and we are going to have some number k that is proportional to the population at the present time. Okay, so we are going to have like population, for example, population now. This will be k time of the so the population, so our future population we can predict through these models. Okay, so and we can derive this using some linear models. Okay, so this is maybe I will just take some example. Okay, so we are going to see the bacteria. Okay, it has an initial number p0, okay, number of bacteria, and then at t equal 1 hour, the number of bacteria measured is 3 over 2 p0, which means it's multiplied by 3 over 2. And if the rate of growth proportional to the number of bacteria, we define bacteria as a function of t, at time t, determine the time necessary for the number of bacteria to triple. Okay, so here we solve by taking the initial conditions. So let's start with t0 equals 0, which going to be start by defining with this. Okay, so p0 is the initial condition, and then by observations, so when t equal 1, this will be 3 over 2 po, right? This is based on the information given, right? And then the differentials will be the dp dt. Okay, we are going to look at with respect to t is equal kp, or we can write that this will be equal to 0. And we can see that by inspections of the solutions, we can see that this is a linear model. This is a linear first order. We can see that we can have our integrating factor that is equal to this, right? So we are going to use the integrating factor as in the first order differential equations, and we can rewrite this and write a product form. So we multiply this to here, and then we can simply write that this is going to be this, right? And then we get integrating this part, we are getting this will be p equal a constant. Okay, or we can write p of t is actually c e k t, which this is actually the formulation that usually comes up whenever we talk about population in general. Okay, so if you remember in biology or even in statistics, we are always approaching the number of population by this method. Okay, so if t equals 0, so when t equals 0, then we are going to have c, e, and then this is k, right? Oh, this is 0, sorry, so it's 0. So this will be equal to c. So p0 or p0, in our case, this is just a constant. So our p of t is equal p0 e kt, right? So we can rewrite like that. Okay, and then at t equal 1, then we have p1 is 3 over 2 p0, right? Okay, so we can write 3 over 2 p0 equal p0 e kt. So we can cancel this, right? And then we have e kt equal 3 over 2, or in our case here this is equal 1. So we can find the k. So k is equal to ln 3 over 2. Okay, and then you can compute using calculator. This will be around this number. Okay, so this whole simulations for these models, we get the final models or final formulations for this part is p of t equal p0 e with power of 0.405 t. Okay, this is the final models. We need to find when bacteria is triple, right? It means that we are going to have this 3PO equal PO E and then write the number T. So now we can find T. So from here we can cancel this, right? So E is equal 3, or this equal ln 3, or T is ln 3 divided by 0.405, or it will be approximating to 0.7 hour. Okay, so this is the answer, but the way we solve it is actually start with this. Okay, so start using the first differential equations, first order differential equations, and it's linear, so we can compute using integrating factor, and then we get these expressions which we are dealing with some initial conditions. Okay, we have it from t equals 0, t equal 1, and then we want to make sure that what is the time needed for the bacteria to be tripled. Okay, and that is one example. We can see from the graph that if we estimate, then this is when it's triple. Okay, so we can see how much we have for the how much time needed for the bacteria to be triple. Okay, and growth and decay is actually the same simulations, but the difference is in k. Okay, the k for growing is positive, but for decay it will be reduced or it's negative. Okay, so I think it depends on what is the condition. We are going to be able to simulate how is, for example, the population grow, or perhaps some radioactive decay. So that is the most common problem within these linear models. Okay. Aside from that, there are also other like a physics phenomenon, but I think just to use the population or decay, that will be, I think, a good method to relate what we have done so far with the applications. Okay, so aside from population or growth and decay, the models for linear models, we can also simulate for several phenomena, like, for example, Newton's law for cooling or warming through this this formulation here, which T and Tm is going to be the temperature, okay, and Tm is the ambient, and T is the one that we are looking for. Okay, this is the temperature of the object, and K also a constant, okay, constant of proportionality. So you can see from here. Also, other phenomenon is mixture. So we have a rate for salt, the input, and then this is the output. Okay, so we are going to have this input minus output, or R in, R out, and it will devise a new equations from there. So for example, perhaps this goes by equations dx dt plus maybe x over 100 equals 6, and you have some initial condition, for example, like this. Okay, it is also able to simulate for many constructions, but usually you can also draw the diagram, like maybe the diagram will be given like how many the input and how many the output, and perhaps they will give you some maybe volume and maybe how fast the rate is, or even maybe the pump, it's like usually using gallon per minute, the rates. So sometimes you given directly, or you need to calculate first, and then you just put all the information inside this formula, and then solve using linear equations. Okay. Or another method is related to the circuits in electrical. So it's either this one or this one. The first one is using the inductor, and it is based on Kirchhoff rules or Kirchhoff law. So it's stated that the second law states that the sum of the voltage drop across the inductor, which is the L. Okay, so you have the di over dt, and the voltage drop across the resistor is the same as impressed voltage E of t of the circuit. Okay, and then from here, and then we can rewrite becoming this. Okay, and yeah, I think at least this is all the examples, but I believe for the first one, since it's very general, you should be able to understand the first one clearly. Okay, because I think the other one, maybe for the Newton's law, it's still not too complicated, but for the mixture or even the series circuits, maybe it's a little bit complicated. If for example you are not also really familiar with the electrics, you should maybe find some of this maybe a little bit difficult. But I think if you understand the Kirchhoff law and understand how the circuit will be, like this one here, there's some illustrations, I think you could also find these examples not too difficult as well. Okay, so all of these are examples on linear models. Okay, there are actually another sections which describing nonlinear models, but I think I will just keep this linear models for just for showing you how we apply the differential equations within some daily life, or even some physics phenomenon or chemical phenomena in our daily life. Okay, so I think that's the additional video. Okay.